So in the last class, we have seen what? We have seen this sharing bridge, how to measure your relative permittivity using sharing bridge. All these things have been seen by us. Okay. So any doubt from the last class? So today we are going to finish this session, means this chapter, as quickly as possible. We have few questions also. So Wagner Earth device. What is this Wagner Earth device? See, when we measure any of the capacitance, okay, capacitance. So capacitance, a 1 farad capacitor, okay, 1 farad capacitor. This is very high value. Have you seen 1 farad capacitor anywhere?
No, sir.
Usually the capacitors that you might have seen, it is in your microfarad capacitance, okay, microfarad. Never ever you will see a capacitor value that is 1 farad. This is very high capacitance value, I am telling you. Okay. Even microfarad is a big unit. So usually what happens when you are measuring capacitance in this micro, so micro means what? Is 10 to the power minus 6. Now when you are measuring something as big as 1, in this context, 10 to the power minus 9 is a very negligible value. But when you are measuring something as low as 10 to the power minus 6, at this time 10 to the power minus 9 is comparable. Okay, 10 to the power minus 9 is comparable. So what happens when we are measuring using sharing bridge? So there are some stray capacitance. Okay, capacitance generated due to your, like, this joints. Okay, this joints, or it can be due to this ground also. Somewhere you might ground this circuit. Let us assume we are grounding this circuit over here. So what happens? There is a negligible amount of current, capacitance, that by default comes over here. Okay, so this is known as what? This is known as link. See, this is one of the link to ground capacitance. This is ground, so this is link to ground capacitance. And the capacitance which has been generated on all these links, like at this point, this point, this point, so these are known as what? Link to link capacitance. Okay, link to link capacitance. So these values are approximately 10 to the power minus 9. Okay, nanofarad, in the range of nano. So when you are measuring a capacitance value, these things, okay, they play a very, means they give us errors. Okay, so we have to avoid these errors. So now what we do? We have Wagner Earth device. So any of these bridges, if you take like sharing bridge, Desotti bridge, or even modified Desotti bridge, all of them are actually connected on this apparatus only. This is your sharing bridge. Now, how does this sharing bridge works? Okay, so let us see. No need to write. You just first understand what is happening. Then you can write it in your own language. Okay, first listen. So this is basically your what? This is your Wagner Earth device. Now it is written in your GATE syllabus that you have Wagner Earth device, but no question has been asked. And I am very much sure no questions will be ever asked also. Okay. So now look, basically here we have two bridges. Okay, two bridges. And what are those two bridges? See, one of the bridge is this one. This is your normal what? This is your normal sharing bridge. This black color one. Okay. So when is this bridge going to be activated? See, First, just listen, then you can note everything. See, when you activate this, you can see basically the bridge connected will be this circuit. Okay, so this is your bridge and this will be your source. Now, what is this? This is not connected. Why? Because here it is open. So whatever voltage difference means voltage is generated over here, it will be just what? It will be V omega. Omega means what? It is the angular frequency of the source. Okay. So this is not playing any role at the moment. Now there is one more bridge over here. And what is that bridge? So look carefully. If somehow I connect this switch over here, okay, I connect this switch over here. Now you can see that this is the bridge. Sorry. Okay, this is the bridge. This is the detector. Okay. So this is your bridge. One more bridge. Just give me a second. So this is the bridge. Okay. Are you able to see both the bridges? Tell me.
Yes, sir.
Okay, so these two are the bridges. Now, how do we basically use to remove the stray capacitance with the help of this apparatus? Now we are going to see. Okay, so when detector, so this is one switch. When detector in position 1, basically it is sharing bridge. Okay, sharing bridge. And when detector in position 2, we have a new bridge. What is that bridge? We don't know. But there is one new bridge that we have. Okay, so what we do, we start from this position 1. Okay, initially we are at position 1. Now listen carefully. We are at position 1. What we do? Initially at step 1, let me name this as S. Okay, this is the switch. Initially, switch is at position 1. So that is your sharing bridge. We balance the bridge. But tell me one thing, when I have balanced this sharing bridge, does it contain stray capacitance or not? Does it contain stray capacitance when I have balanced the bridge? Obviously, stray capacitance is going to be present. Why? Because I haven't done anything. It is just a simple sharing bridge. So stray capacitance is present. Now, how do we remove it? So already the bridge has been balanced. Okay, bridge has been balanced. Now, what are we measuring over here? What are we measuring? We are measuring this C1. Okay, we are measuring this C1. So we have to nullify the effect of stray capacitance on this C1. Understood? Tell me yes or no. Is it clear what we are trying to do at this point? Okay, so obviously at this point of time, C1 has the effect of stray capacitance. Okay, stray capacitance is there. Now what we do, we change the switch position to S2. We change the switch position to S2. Now where are the stray capacitance? First tell me. Stray capacitance are present over here or over here, here, okay, or over here, here. All these places stray capacitance are present. So now what we do, we change the switch position to S2. The moment I change it to S2, So this is RW. It's looking like omega. RW and this is CW. See, this is my W and this is my omega. Okay. So what is this RW and CW? So the moment I change the switch position to S2, this new bridge is known as Wagner Earth device. Okay. This is known as Wagner Earth device. So this bridge, see, previously I forgave, means I didn't tell you. See, when I had taken this bridge initially, okay, I had written balance the bridge. So this bridge means when we were at S1, our bridge was balanced. But the moment I changed this S to 2, now it's a new bridge because one of the arm is RW, another arm is CW, another arm is C3, and this is R4 and C4. Now, basically what we do, please listen. The moment we change this switch position to 2, now my bridge is unbalanced. Up to this point, tell me, is it clear?
Yes, sir. Yes, sir.
Okay, bridge is unbalanced. Bridge is unbalanced. Now, when the bridge is unbalanced, don't disturb R4 and C4. What are this R4 and C4? Basically, R4 and C4 are the variable parameters for balancing the sharing bridge. So sharing bridge, it is balanced by manipulating R4 and C4, whereas Wagner Earth device, it is manipulated using RW, it is balanced using by manipulating RW and CW. Don't disturb R4 and C4, balance the bridge using RW and CW. Tell me, is it clear? Is it clear? So I balance this whole bridge using RW and CW. Okay. So now this bridge is also balanced. Now what we do? Once again, we change this to S3 I have written. Once again, we change it to S1. Now, the moment we change it to S1, what will happen? Once again, this bridge will be unbalanced. Okay. But the unbalance will be slightly more or less compared to this S1. Why? Why will it be so? Because I have reduced some of the effect of this stray capacitance. I have reduced some of the effect of stray capacitance with the help of this Wagner Earth device. So there will be a small unbalance once again. Okay, so now we don't disturb RW and CW. Once again, we are going to balance this bridge using R4 and C4. Then once again, we switch to S2. You will be seeing that this time when I switch to S2, the balance will be very less. And this process we keep on doing until and unless both the bridges, the sharing bridge as well as the Wagner Earth device, are simultaneously they are balanced. The moment Wagner Earth device and sharing bridge are simultaneously balanced, all the stray capacitance has been nullified from this bridge. Tell me, is it clear? Any doubt? So simultaneous means alternately we bring the bridges to balance position until both the bridges are balanced. Is it clear? Any doubt? Tell me. Clear? Then kindly note this down. Whatever I have said, note quickly. So first note this diagram. Okay, when you note the diagram, then you can note this theory part also. So Wagner Earth device, it is basically used to do what? It is used to discharge the value of stray capacitance. So I will write it over here. Shishir, you are from electrical. So this time paper
Yes,
is going to be
yes,
very
yes,
good. Okay. So take care of that.
yes.
Even instrumentation also. And one thing I will be very clear with you guys. See, as you guys are preparing solely for GATE, okay, means you are not even in your college or working anywhere. So please, I have huge expectations, okay, that you are going to study. See, getting result is a different thing because in those 3 hours, note also and listen also, okay. So getting result is a different thing, okay. Why? Because in those 3 hours there are different factors that are going to play. Maybe you might be nervous, okay. There are different things that might go wrong, and I am okay with that. It might happen. So Nitish, how many times have you given GATE exam? Is this your first time, second time, or third time? And Shishir, same question.
So second time it will be.
Nitish, what did you say? I couldn't hear you.
This is my second time, like properly preparing. This is my first time actually.
Okay, fine. So you have given the GATE exam. Okay, so that is okay. So okay. So what was I saying? Yeah, I forgot. What was I saying? Yeah. Anything can go wrong in while you are writing the examination. It's okay. It doesn't matter that much. If you are preparing, see, you are your best judge. Okay, you will know that yes, I have given my 100% effort. So are we doing that? You don't need to answer me. You don't need to answer me that whether we are doing it or not. You can answer it to yourself only, that are you responsibly with 100% dedication, are you preparing? So you have your answer. Okay, if the answer is yes, then continue with that pace only. If the answer is no, then you yourself have to find out why it is no and where are you actually lacking. So you have to find out. Okay, because I am very straight, I will say it very straightforward. Okay, you guys are wasting your 1 year. It's like that only. Not means I cannot be that much raw. It's not like wasting. You are doing something actually sitting at home and you are just solely preparing for examination. Even I have done the same. Okay. Back in 2013, I got ranked like 2000 something. Okay. And then I prepared 1 year, not even 1 year, for 3 months I have prepared. Okay. Because my TCS joining was in November and I was sitting at home, so there was no work. I got means my degree at in August month, okay, August 2013, and joining was in November. So I was like, "Acha, ab kya karu, kya karu, kya karu." So all my friends were preparing for GATE, so I also went with them, started preparing, but I was not studying that much seriously. Then November I started studying seriously means okay. Someone told me bad that I am not good at studies and all those things. So I felt really very bad. कि यार हमेशा लोग and yes I was not very good at studies. Okay, means I have passed with very less mark also in BTech 7.49. So I was like average student. So someone told यार तुम तो पढ़ते लिखते ही बिल्कुल नहीं. I felt very bad because the guy told me in front of like 100 people that you are very bad in studies. So I felt very bad. I started preparing कि नहीं, at least I should prepare. So I prepared and I cracked GATE exam. So when you are truthful to yourself, result doesn't matter. Okay, so be truthful and prepare very, very well. As you guys are dedicating just 1 year of your life to this exam. Okay, so out of your life of 80 years or 90 years, you are giving just 1 year. Okay, 1 year to this exam. Suppose I give you 10,000 rupees and I tell you, Shishir, Nitish, you stitch one cloth for 5,000 rupees. So it's like that. So you make that 5,000 rupees dress very, very, means what? Forgot the exact term. Means very, very trendy kind of. Okay. So this is your one shot to get into IIT or in PSU, which whatever you desire for. Okay. So make it fruitful. That's it. चलो आगे बढ़ते हैं. Have we noted this down? Okay, so let me ask, are we preparing dedicatedly? Means now you can answer it to me. Yes or no? Honestly. Okay, honestly answer me. Yes, that is what I want. If it is yes, very good. Keep up the pace and keep going. And wherever you face doubt, whether it's my subject or someone else's subject, you let me know. Okay, you let me know. Whatever, how much I can help you, I will try to help you. Okay, chalo. Now let us move to Wayne's Bridge. Okay, what is this Wayne's Bridge and where is it used? So Wayne's Bridge is basically used for the measurement of fundamental frequency. Now what is this fundamental frequency? Have we studied signal systems? Signal system. Okay, so any wave. Okay, first tell me this. Is this signal an AC signal? Huh? Nitish, what about you? No. Shishir, if no, why no? Why are you telling no? So AC signal, okay, let me tell. AC signal are all those
It
signals.
was no
What?
for the previous question.
Okay, so अच्छा ठीक है. It was no for the previous. So now you are telling yes. So AC signal are all those signals. Okay, all those signals whose average value over a time period is zero. So this is an AC signal. But then, why don't we use this AC signal in our home? Why don't we use it? Why don't we use this? Can you guys tell me? P average is zero. ये क्या हो गया? So P average is zero. What? Why this one? Why P average zero? कुछ भी मतलब. So we usually don't use such kind of signal. I will tell you why. Because this square wave, it has multiple frequencies in it. If you remember Fourier series, especially trigonometric Fourier series. So this is one odd signal. This is one odd signal. It will contain basically harmonics of sine. Okay, it will contain all the harmonics of sine like sine omega naught t, sine 2 omega naught t, okay, sine 3 omega naught t. All those frequencies are going to be present. So when you have multiple frequencies in the signal, it is very difficult, okay, very difficult to use it in your home appliances. That is why we use either sinusoidal signal or cosinusoidal signal, which has angular frequency, linear frequency as approximately 50 hertz. Okay, 50 hertz. Okay, that means what? 100 pi or 314 radian per second. So we use a single frequency line. So then what is this fundamental frequency? Fundamental frequency is this frequency, particularly the frequency whose multiples we use in trigonometric Fourier series. Tell me, is it clear? What is fundamental frequency and why are we, means what are we measuring over here? Any doubt? See, this square wave is basically made up of something like this. If you break it, sorry. Now this red color sinusoidal, it is your fundamental frequency. Now there might be one more signal. See, this is sine omega naught t. Whatever is the frequency of the square wave, same is the frequency of the sinusoidal. Now there might be a signal which is like this. So now this is what? This is sine 2 omega naught t. It has double the frequency of the fundamental frequency. Now there might be a signal which is sine 3 omega naught t. So now how will I draw it? Means it's okay. You have understood basically what is happening. Tell me, is it clear that what we are trying to find out? Okay, fine. So basically Wayne's bridge is used to measure what? It is used to measure. So Nitish, were you able to solve those two questions which you had asked for network?
Yes, sir. I was able to solve.
Okay, very good. Acha. So Wayne's bridge is used in the measurement of fundamental frequency. Sometimes it is also used as feedback for RC oscillators also. Feedback for RC oscillators. Okay, RC oscillators. And when you study control system, it will be taken by me only. When you study control system, once again we are going to see this Wayne's bridge in your lag compensator. Now I will show you. Okay. Now what is this lag compensator? At that time we are going to discuss. At this moment it's okay, just keep it noted. Later on we are going to see. Okay. So it is used to measure the fundamental frequency. Now here you should be knowing that this omega is unknown. So we have to find this omega. Okay. Omega is unknown. So what we do, basically we start using this bridge and we start at balance condition. We bring the bridge to balance condition. Okay. At this moment we don't know what we are manipulating or how we are manipulating. We are just doing what? We are bringing the bridge to balance condition. What will happen at balance condition? Okay. At balance condition. So at balance condition, let this be Z1, this be Z4, this be Z3, and this is Z2. So Z1 into Z4 is equal to Z2 into Z3. So this will be R1 plus 1 by j omega C1 into R4 is equal to Z3 is R3. This is R2 divided by 1 plus j omega R2 C2. Okay, R2 C2. Fine. So what we can do over here is, so what we should do, so I am trying to think. Okay, let me do cross multiplication. Okay, let us do cross multiplication. Cross multiplication will R2 R3, this is okay. Or else it's okay, let it be like this only. R1 into R4 minus 1 by j omega C1 is equal to R4. Fine, and this will be R2 R3 1 plus omega R2 C2 whole square, and this will be 1 minus j omega R2 C2. Okay, let me check once. Yeah, everything is fine. Okay, so now let us do what? Let us separate the real part and imaginary part. Okay, so at balance condition, if we do, so R1 R4 is equal to R2 R3 divided by 1 plus omega R2 C2 whole square, and if I separate the imaginary part, so this will be R4 by omega C1 is equal to R2 R3 1 plus omega R2 C2 whole square, and this will be omega R2 C2. Tell me, is this clear? Is it clear? Any doubt in this? Okay, fine. Okay, if this is the case, then what we can do now, see, 1 plus, see this term 1 plus omega R2 C2 square, this is appearing in both the term. If some way or the other I can just manipulate this part, then solving will be easy. So what I do, look over here, R2 C2 whole square is equal to what? R2 R3 divided by R1 into R4, equation 1. Okay, and now this equation 1 I am going to plug it over here. Okay, so if I plug it over here, so what will happen? R4 by omega C1 is equal to R2 R3 divide, what is happening? R2 R3. So this value, now I am substituting this value, R2 into R3 divided by, so I am bringing it in the numerator, R1 R4 into omega R2 C2. So now I can cancel this term. Okay, R4 also cancels. Anything else that we will be able to cancel? No. So now what do we get the value of omega? So omega, okay, omega square, sorry, omega square is equal to 1 by C1, C1 is present, R1 is present, R2 is present, C2 is present. So omega is equal to what? Omega is equal to 1 by under root of R1 C1 R2 C2 radian per second. Tell me, is it clear? Is it clear? So now, which parameters can we manipulate over here to bring the bridge in balance condition? Tell me. So these two equations we have. I told you previously that variable capacitance is costly compared to variable resistors. So here you can see that if somehow if I do what? Look over here. This R1 is uncommon in this equation. It is not present over here. And over here, R4 is present. And here also R4 is present. Okay, R4 is present. So what I do, first we manipulate R4. First manipulate R4 and bring the bridge to the maximum position near to the balance condition, and after that you manipulate R1 to bring the bridge to the final what? To the final balance position. Tell me, is it clear? Is it clear? Now don't tell me, sir, this R1 you only told. This R1 is actually the capacitance, inbuilt resistance of this capacitance. Yes, I know. But here also there is one apparatus that I can introduce external resistance. Okay. So now this R1, you can assume it to be as R1 dash plus small r1, where this R1 dash, it is the inbuilt resistance of this capacitance, and this small r1 is the external resistance I have introduced in this arm. Tell me, is it clear? Is it clear now? Any doubt? So now when we do lag compensator, at some place you are going to get this expression. Okay, you are going to get this expression. Just write it down. Later on I am going to discuss. Okay, so this is the value of unknown omega. It is basically what? It is under root of R1 C1 R2 C2. Okay, any doubt? Any doubt? Okay, so now what might happen? What might happen if R1 is equal to R2? Let us assume this as R. And C1 is equal to C2 is equal to C. Okay, so this will be, then expression will be equal to 1 by under root of R square C square, or this will be 1 by RC radian per second. Okay, radian per second. Okay, if this is the case, that omega is equal to this, then plug it in this equation 1. Okay, put this condition in equation 1. So what will happen? 1 plus omega value is 1 by RC, 1 by RC into R2 value is R, C2 value is C. So this is also RC whole square is equal to R2 R3. So R2 is R. Okay, so R2 R3 I haven't taken. So this is R. Fine. Let this be R3, and R1 value is also R. This is R4. Okay, this is R4. So now RR gets cancelled. This RC gets cancelled. So this is equal to 2. 1 plus 1 square is 2 is equal to R3 by R4. See, this is very, very important. Why is this important? See, making this is not possible. Why? Why is this not possible? Can you tell me? Why I cannot make Something like this. Tell me, please. Because you can see that I have taken R1 as variable. Okay, R1 I have taken it as variable. So how can I make R1 equal to R2? R2 is fixed. R2 is fixed. I haven't kept this R2 as changing. But if I somehow make the ratio of R3 by R4 is equal to 2 somehow by doing what? Let this R4 be constant only. Okay, let R4 be constant. If somehow I am able to balance this bridge only by manipulating R1, and if my ratio of R3 by R4 is equal to 2, then automatically you can see that R1 is equal to R2, it will be same value, and C1 will be equal to C2, it will be same value. The balancing will happen for this condition. Did you understand what I am trying to say? Did you understand? Tell me, Nitish and Shishir, both of you.
No, sir, I couldn't understand the last part.
See, I am telling what? Understand like this. If, see, this bridge, which is the uncommon term out of this two? R1. If suppose R3 is what? R3 is 10 ohm. Assume. Okay. So what I do, this R4, I manipulate it and I make it 20 ohm. Okay. While balancing the bridge only, I said this, if suppose this is my galvanometer or detector, and initially the pointer is at this position. Now what happens? Let us assume initially R4 was what? R4 was 15 ohm. This is just one example. Okay. Now what I do, I saw that when I start increasing the value of R4, what happens? This is coming at this position. So I start increasing. Now at particular point, let us assume 20 ohm. This pointer is at this position. Now if I keep on increasing 21, 22, you might see that the bridge is still converging, but I won't be increasing the value. Okay, I will keep it at 20 ohm only. And what I will do, now I will start to manipulate the R1. Now why am I doing so? Because I got one very interesting result, that when I keep the ratio of R3 by R4 as 2, okay, when I keep the ratio of R3 by R4, sorry, here it is half. Okay, ratio of R3 by R4 is half. Okay, so I have taken one wrong thing. So let me erase this example, please. Let this be 100, and initially let us assume that this is at 40 ohm. Okay, initially R4 is at 40 ohm. So when this is the case, my pointer is in this position. So what I do, I start increasing R4, and I am seeing that it is moving towards balance position. So at particular 50 ohm, I will stop. Even if the bridge is balancing more, suppose if for 55, the pointer is coming over here, it's nearer to the balance position, still I won't go for 55, I will keep this at 50. Why? Because I saw one very interesting thing, that whenever ratio of R3 by R4 it is equal to twice, at that time the value of R1 and R2 is equal to R. Now why will this help? Because you can see this R2 is known to me, so what I need to do, I need to manipulate this R1 or this combination particularly to this value. So immediately what I can do, I don't need to even calculate any further. I know this value of R2. So if I just set the value of this R2 equal to this, then my bridge will be automatically balanced. Tell me, is this clear? Now is it clear?
Yes, sir.
Yes, sir.
Okay, so this is the advantage of knowing this. Okay, is it clear? Any doubt now? Okay, fine. So now why did I tell that this bridge is actually used to measure fundamental frequency? Why? Because if there are harmonics present, so these are my harmonics. Array. So I have erased it. So if you remember, I had drawn one square wave. This is the fundamental frequency. So these are the harmonics, okay? 2 omega naught t, 3 omega naught t. So these are the harmonics of fundamental frequency, okay? So we cannot measure fundamental frequency. Why? Because your bridge will never come to balance condition, or it will never converge when you have harmonics present. So this is actually one drawback of Wayne's bridge, that over here you can only measure frequency of sinusoidal signal or cosinusoidal signal, or to be precise, you can measure the frequency of a signal which has only one frequency content. Okay, so now such kind of signal we usually don't find, because even the practical sinusoidal signal that we use in our home, there are harmonics present. Okay, there are some harmonics present. So that is why the frequency that we get, it varies somewhere around 45 hertz to 52 hertz. Okay, somewhere around, it varies around this frequency range only. So that is why we say that it is around 50 hertz. Okay, any doubt in this? So this is the drawback of Wayne's bridge, that basically what happens, we can measure only single frequency content signal. Okay, any doubt in this? Fine. So with this we end our bridge circuit. Okay, bridge circuit is over. So have we solved this question? All these questions? So this is very important. Did we solve? Nitish, no, for which one? Did we solve the question?
This particular one, sir. I couldn't
Arey,
solve.
batao. Ishir, what about you? First and arey, why first and last one? Last one you have solved. So what is the answer for last one? Let me know. This one is the last question. So you only said first and last one you solved. Acha, you didn't solve first and last question. First question is what? This one.
Yes,
First
sir.
and last. This one you didn't solve.
So I was solving, but I didn't get the answer.
I will tell. Whatever you have done, apply one KVL in this loop. Whatever you have done, I know where you are stuck. Why you were not able to get something? Because you were confused where to do, how to calculate VN, where to Thevenize the circuit. You don't need to Thevenize. Whatever value you are getting, apply one KVL in this loop. Tell me now. Now, are we getting some hint? Tell me yes or no.
No, sir.
Okay, fine. So we will do what? So this question is solved.
Yes, sir.
This is solved. Okay, fine. This is also solved.
Yes, sir.
This is also solved. You are telling this one you couldn't solve. So where are you stuck in this question?
The AC manipulation that I,
What?
the AC analysis of this part, I don't understand.
Why don't you have to do? Why you have to do AC analysis at this point? This is simple bridge circuit. You have to find the value of VRMS. Now what is VRMS? VRMS of this voltmeter. Okay. So what are you going to do? Is this bridge balanced? Okay, we will solve this question only. Okay, we will solve this question. So let me ask you first, tell me, is this bridge balanced or not?
No, sir, because the phase balancing is not balancing difference.
Okay, we will see. So if you see, most of the students, what they know, let us assume this is Z1, this is Z2, this is Z3, this is Z4. In most of the coaching and most of the time, even we have seen Z1 into Z2, sorry, Z1 into Z4 is equal to Z2 into Z3. We take it like this. So if we take this is J into J is equal to J into J. Minus into minus, so that will be plus. So you can see this will be what? This will be minus 1 is equal to minus 1. Array, bridge is balanced. Bridge is balanced. Okay, so whenever bridge is balanced, what you are going to write? Okay, so if bridge is balanced, so VRMS is going to be 0. Okay, VRMS is going to be 0. So now if you write the answer 0, you will also get 0 mark. Okay, 0 mark. Why? Because this has two parts in it, magnitude condition and phase condition. And I told you, whenever the branches of bridges are ideal inductor or capacitor, you have to check for magnitude and phase condition. So if you check the magnitude condition, so magnitude of J means magnitude of Z1 into magnitude of Z4 is equal to magnitude of Z2 into magnitude of Z3. So if you check, so you are going to see this is 1 into 1 is equal to 1 into 1. So this is okay. This is fine. Magnitude condition is being satisfied. But what about phase condition? So phase condition, if you see, so this is equal to what? Phase of this one is plus 90. Phase of this one is also plus 90. Means these two are multiplied, na? So that is why I am adding the phase is equal to minus 90. Okay. So here at this particular point, if you had written 0, so you won't get 0 mark. Either you will get 1 mark if it was 1 mark question or 2 mark. Okay. So you will get this. Why? Because even phase condition is over here at this point, it is equal. 180 degree is equal to minus 180 degree. See, this is plus 180 degree. If you go in anti-clockwise. Now, if you move in clockwise direction, this is minus 180. So both of them are same. Both of them are same. So here 0 is correct. I think somewhere I might have made a mistake. So I was framing this question. So what we can do, if I bring it over this side, so then, yeah. So yes, still you can see magnitude condition will be satisfied, but phase condition at this particular time, it will be not satisfied. Why? Because if you solve, once again it is going to be, oh, it is going to be satisfied. Okay, I have to rephrase the question once again. So what I can do over here is, Wait, let me pause the recording. So what I was telling, that this 180 and minus 180 degree, this is what? This is not same, but it is representing the same axis, same angle, but here it is not same. Why? Because the way in which we are representing it is different. So that is why your bridge is unbalanced at this point. Why it is unbalanced? Because due to the phase condition. Okay, due to the phase condition it is unbalanced. So now we have to find VRMS. So now it is very simple. What you can do for finding VRMS? So if you have to find VRMS, so just try to find out this current. If you are able to find out this current in sinusoidal, so this will be also sinusoidal current only. Sinusoidal current. So RMS value will be Im by root 2. So when you get Im by root 2, this, if you take this as A point, this as B point, you will be obviously getting what? You will be getting VAB minus VB as your what? As your VRMS value, where VAB will be equal to Im by root 2 into minus J, and VB will be equal to Im by root 2, and this is plus J. So if you solve this, you will get one answer. But one thing to remember, that RMS value, or else it's okay. Let us solve it only. I will solve it for you only. Okay. So, okay. So this bridge, I told what? It is unbalanced bridge. Okay. It is unbalanced bridge. So tell me one thing. Tell me one thing. If it is unbalanced, what about this voltmeter? What is the resistance of this voltmeter? See, if bridge is unbalanced, that means what? There will be voltage generated. That means there will be some current flowing. Are you understanding the question? Tell me yes or no first.
Yes, sir.
Okay. So first thing, you need to calculate whatever is the actual impedance of this branch. And for calculating the impedance of this branch, because I want to find this current I. Okay. So you need to have impedance, but here there is no resistance value of this voltmeter. If nothing is given about voltmeter, then you have to assume that voltmeter has infinite resistance. Infinite resistance. Okay. Infinite resistance. If that is the case, then you can see basically J means this two branch, means this two element are in series, J minus J, and this is also in series, minus J plus J, and both of them are in parallel. So you can see this is basically what? This is 0 parallel with 0, so that is 0. Now what is this condition? What is this? What is this?
Short circuit.
Short circuit.
This is simple short circuit. Okay, this is simple short circuit. It is just a short circuit. So what will be the current? I is equal to voltage 100 sine omega t divided by 0.5. So I is equal to 200 sine omega t. Now I have to find this value of voltage. So V is equal to, means this V, okay? V is equal to, it will be what? I into minus J minus I into plus J. So this will be I common. This will be into minus 2J. Okay, minus 2J. So this will be minus 400J. Okay, minus 400. Wait a minute. Is it correct? Array. Once again, I am making a mistake. So that is what I was thinking. See, This current is what? 200 sine omega t. Okay, 200 sine omega t. Let this be I1, this be I2. So now this is short circuit. So what I assume that full current is flowing like this. No, these all elements are present. So equal amount of current is going to flow from here 100 sine omega t and from here 100 sine omega t. Okay. So these two are flowing like this. So now if I want to calculate VAB, so that will be equal to 100 sine omega t into this minus j minus 100 sine omega t into plus j. So this will be 100 sine omega t into minus 2j, or this will be minus 200j sine omega t. Now we have to measure RMS value. RMS value. So RMS value cannot be negative. We just have to take this value. So it will be what? 200 by root 2, because this is sinusoidal signal. So this is what? This is okay. One thing, let me ask you, what is this 200 minus j basically representing? What is this representing? See, basically, if you want to write this voltage, I will tell you. So if you want to write this voltage is basically like this, 200. Okay, 200 minus j. What is the magnitude of minus j? It is 1. What is the phase of minus j? It is minus 90 degrees. So this will be sine omega t minus 90 degree. And what is this? What is this? This is basically minus cos omega t. So this will be minus 200 cos omega t. So the voltage that is present in sinusoidal value, it is minus 200 cos omega t. But if you take RMS value, root mean square. So in root mean square, first you square the signal, then you take the mean of the signal, then you take root. So when you square it, this will become positive. So root mean square of 200 cos omega t, it will be same as minus 200 cos omega t. And what will be that value? It will be 200 by root 2. So whatever is this value, you have to write it down. Okay. So I guess I can write it like 100 into 2 by root 2. So this is root 2. So root 2 is 1.414. So this will be 141.4 volt. So this is the RMS value that will be shown over here. Tell me, is this question clear? Is this question clear?
Yes, sir.
Sir, in case the voltmeter has got some resistance in question it is given, then we can find the RTH and then solve it.
Yes, then you need to find RTH. Then you have to find RTH from this point and VTH also from this point, and then you have to apply voltage divider to get this value. Okay, you have to get this value, because then your equivalent circuit will look something like this. You will have some signal, you will have RTH at this point, and then you have the resistance, not RTH, this will be basically ZTH, because all the elements are basically what? They are complex. And here you will have RTH. So you have to find this voltage, okay, this voltage, and then take RMS value of this voltage. Is it clear?
Yes, sir, it is.
Okay. So now what we will do, as you haven't solved these questions, so first try all this question. Who has not solved? Nitish, I think. Okay, Nitish has not solved. So
No, sir, that is solved.
which one is solved?
Like the rest of the questions.
Rest of the question you have solved.
Yes, sir.
All of you have solved the rest of the questions.
The first question, this one, I didn't get the answer. Rest I have
Remaining
solved.
all the questions you have solved.
Yes, sir.
तो गुड है. Why we were not able to solve this question? Chalo. This is also simple question. So what is given? In the Wheatstone bridge shown below, galvanometer G of current sensitivity 1 microampere per mm. So galvanometer sensitivity is what? It is 1 microampere per mm. That means what? If this is the galvanometer scale, so if this is suppose 1 mm, okay, 1 mm. So if your galvanometer points from here to here, that means it is indicating a change in 1 microampere. If suppose for this indication it was 0 microampere, then for this indication it will be 1 microampere. That is what is said. Okay. A resistance of 2.5 kilo ohm and a scale resolution of 1 mm. So obviously here if the sensitivity is given is 1 microampere per mm, so the scale resolution, the resolution of the scale is what? 1 millimeter. Okay, because here you can see the minimum, what is the sensitivity? It is 1 microampere per mm. So you are measuring in terms of mm. That means in this scale the minimum that you can measure is 1 mm. For 1 mm you are measuring 1 microampere. So that is what is said. Scale resolution. Scale resolution means of all this markings. Okay, so there can be only change in 1 mm. Let del R be the minimum increase in R. Del R is the minimum increase in R from its nominal value of 2 kilo ohm. So initially this is 2 kilo ohm. There is some nominal change del R that can be detected by this bridge when R is 2 kilo ohm plus del R. What is VAN? Okay. First tell me, did we understand the question or not? Tell me this.
Yes, sir.
You understood that basically this del R is what? This del R is coming when this galvanometer is reading a current of 1 microampere or when this galvanometer is at this position, because initially when this R was at 2 kilo ohm, so you can see this bridge is balanced, 2 into 6 12, 3 into 4 12, bridge is balanced, I galvanometer is 0. But the moment here it is said that a minimum, nominal minimum change in R is done, R plus del R. So when I do R plus del R, that means the minimum current this galvanometer is detecting. And what is the minimum current this galvanometer can detect? Initially it was 0 microampere. Next it will be 1 microampere. So basically this 1 microampere is the current due to this unbalancing factor del R. Okay, tell me, is this clear now? Is it
Yes,
clear?
sir. Yes, sir.
So we have to find this value of del R. So that means current flowing through here, it is what? 1 microampere. 1 microampere current is flowing through this branch. Okay, fine. From here it is 15 volt. Okay. Anything else we have been given? So this is 15. Okay. So this is what? This is 2000 plus del R. And what is given? 1 microampere per mm. Okay, fine. 2.5 kilo ohm. Okay, a resistance. Okay, here also it is given 2.5 kilo ohm. Okay, 2.5 kilo ohm is also given. Anything else that has been given? Okay, fine. So now what we need to do is, so this is Ig. Let me assume this current is I1. Okay, not. Let me assume this current is I. Okay, this current is I. If this current is I, let this be I1, this be I2. Okay, So you can see from here, basically it will be what? It will be I1 minus Ig, and from here it will be what? It will be I2 plus Ig. Okay, I2 plus Ig. So this will be over here I2 plus Ig, and here it is. So once again you can see that this will be I1 plus I2. Fine. So now I have to find what? I have to find this value. Okay, so Ig, you can see what? Ig is 1 microampere. Already it is given. So now simply apply KVL. KVL in which branch? Somewhere. Okay, yes, very good. So let us first apply KVL in this loop. In this loop. In this loop, okay? So it will be what? Minus 15 plus 3 kilo ohm into I1, and from here it is what? Plus, or we could have even used this one, or else it's okay, let us use this only. 2 kilo ohm plus del R. See, this del R is also in kilo ohm at this particular point, okay? Into I1 minus Ig. I1 minus Ig is 1 microampere. So this is very difficult to solve. Wait, let me see if I can do something else. Wait a second. So this is 2000 plus del R into I1 minus 1 into 10 to the power minus 6 plus galvanometer resistance is given as 2.5 kilo ohm plus 2.5 into 10 to the power 3 into 10 to the power minus 6 plus VAN. Okay, VAN. So it's okay. So VAN is equal to minus 2000. How can I find this del R? This is the question. Somehow if I am able to manipulate this del R,
Sir, we can Thevenin's the galvanometer part and find delta.
pardon,
We,
I couldn't hear you.
we can Thevenin's that across the galvanometer and find delta. Like we know Ig, so uh, we can get VTH upon RTH plus RG. So
No,
then we'll
no. Basically, it is, we don't even need to Thevenin. See, you can do one thing. Means I was actually thinking somehow if I can use this loop. So you can use one of these loop. Okay, use this loop. You will get I1. And then if you apply loop in this, you will get this value of VAN. Okay, so that is what I am trying to do. Okay, let us solve. It's okay. Why to get scared? I1 minus 1 into 10 to the power minus 6 plus 2.5 into 10 to the power minus 3 into 10 to the power minus 6. Sorry, this will be also, or else wait, let me solve this question once again. See, first time I am applying KVL in this loop. Okay, KVL in this loop. So it will be minus 15 plus 3 kilo ohm, matlab 3000 into I1, and this will be what? Plus 2000 plus del R into I1 minus Ig, okay, is equal to 0. So this is 1. So what I can do over here is that approximate I can do. Still, if I do this, there is some issue going on. Where are we getting stuck? Somewhere if I can substitute something. I have been asked to find this value of VAN. बताओ. See, I'm very, very sorry. First, apply one KVL in this loop. In this loop. Okay. So what it will be? So this is all about KCL, KVL. So minus 3 kilo ohm into I1. Okay. Plus 6 kilo ohm in 6000 into I2. Okay. And I am going opposite, so this will be minus 10 to the power minus 6 into 2.5. So 2.5 into 10 to the power minus 3. Okay, so what value do we get over here?
Sir, it is 2.5 kilo ohms.
Okay, yes, sorry, 2.5 kilo. So we will be getting 6000 I2. Wait a minute. So while applying this one, I2, but then once again I1 will be present. Where we are getting stuck, this is the question. Six thousand I2 is equal to 3000 I1 plus this will be what? 2.5 into 10 to the power minus 3. Fine. So this will be one equation. One more equation we can take from here. Okay. So minus 15 plus 6I2 plus VAN is equal to 0. Now 6I2 is this. 15 is equal to 3000 I1 plus 2.5 into 10 to the power minus 3 into 6 plus VAN. Now somehow I need to find this I1 the easy way. This I1, why am I not able to get? See, we cannot Theveninize also. Why? Because there are two constraints. This del R is also present. There is something hidden over here which we are not able to find out, and that is Where are we getting stuck? Wait, let me pause the recording. Okay, so what we did, we applied node. Who told me this method? Who told me? Shishir or Nitish?
Yes, sir.
So very good. Since I was struggling, really. So sometimes these all things happen in examination. You can see this was just a one-line question, but if this same question was in examination, even if myself being a teacher, I would have struggled like for 15 to 20 minutes, and this would have broken my motivation. Why? Because this is simple KCL KVL. And yet it was, means I was struggling at this point. Now I can solve really difficult question, but this simple question, it was very, very frustrating for me to solve. Okay, fine. So we found out this one, that it is 6.24. Okay, any doubt in this? VA is equal to this value we got.